Today, we're going to start off with two keynotes, and I am delighted to be able to introduce the first of those keynotes this morning to you. And the first of those is Dr. Kristina Johnson, and she is the 16th president of The Ohio State University. I will give a brief resume of Dr. Johnson, but just note it'll be abbreviated because it is a very long one indeed. She was previously the chancellor at State University of New York, SUNY, and she has served and founded as CEO in several successful science and technology companies. And she has served as the Undersecretary of Energy at the U.S. Department of Energy, where I first met Dr. Johnson, and we had a long and rich and very, very productive relationship, and one that I really, really cherish. Thank you, Christina, for all the wonderful support that you gave me when I was at the National Renewable Energy Lab. I really, really appreciate that. Dr. Johnson has published over 150 refereed papers and proceedings, holds more than 100 U.S. and international patents. Along with the John Fritz Medal, her awards include the Dennis Gaber Prize for Creativity and Innovation in Modern Optics, the Society of Women Engineers Lifetime Achievement Award, and the Woman of Vision Award for Leadership by the Anita Borg Institute of Women and Technology. She's a member of the National Academy of Engineering, the National Inventors Hall of Fame, the National Academies of Inventors. She's also an inductee of the Women's Technology International Hall of Fame and fellow of the Optics Society of America and the Institute of Electronics Engineers, the International Society for Optics Engineering, and I could go on and on and on. She received her BS, MS, and PhD from my other alma mater, the Double Eber department at Stanford University, and she was a varsity athlete there in field hockey, founded the club varsity lacrosse team, and she was named among the 40 years of Title IX, 40 women who have made an impact by the Women's Sports Foundation, ESPN Plus, and Women in Cable Telecommunications. She's got a number of honorary degrees. Anyway, good friend, wonderful example of engineering at its best. Dr. Kristina Johnson, thank you for being here. The floor is yours.
Dan, it's so good to see you again and have a chance to catch up briefly right before the start of the symposium. I'm delighted to join this symposium on engineering's impacts on society and the role, particularly of the National Science Foundation in those impacts. I'm so glad to have the opportunity to speak to science and engineering teachers and professors and students at all levels. My own time as a student led to an absolutely thrilling career as an electrical engineer, and it's taken me from academic research to entrepreneurship to the Department of Energy, where we spend a lot of time together, Dan, and then to academic leadership now. Today, I'm going to talk about that journey because it illuminates some of the themes that I think will be useful for next generation engineers who are ready to roll up their sleeves and get at some of the big problems that we're facing, in particular climate change and the vulnerability to infectious disease. So I just start out with this picture, and this picture is a photo of my dad. It's my dad shaking hands. He's on the left. November 1967. Wow. It's important to me because my dad was an electrical engineer. And what he taught me is what engineers do is we do big projects. Mm-hmm. Nobody else does big projects than us. I mean, we lead big projects. I mean, people do big projects, but we lead them. And my dad and my granddad, who actually is a Buckeye, went to Ohio State, were both electrical engineers, and they both worked at Westinghouse. In fact, my granddad worked for George Westinghouse. So I think that my path to becoming an engineer is because I wanted to know more about what my dad did. And my dad told me that's what he wanted, to learn more about what his dad did. So anyway, it all kind of started back in the day. So I started to do little projects in high school. I was fascinated by holograms. And I think back when I was in high school, so in the sort of early 70s, holograms were not as prolific or endemic. They weren't everywhere like they are today. Mm-hmm. The project that I chose to do in high school was a double exposure experiment. So you take one picture and then something moves, and you take another picture, and that interference of the motion, you can actually see how much it moves. So I actually took a double exposure hologram of a fungus and ended up winning the city, the state, and a first and second place at the International Science Fair. And that's important because that was my first lesson into how to build confidence. do a project, do something that hadn't been done before, do something that's hard. And it just really helped me build confidence. So when I went to Stanford in the fall of 1975, I had my little holograms from this project, and I went knocking on doors of professors who did optics and holography. And I found a great professor, and in particular, that was Joe Goodman, and he's now professor emeritus at Stanford. And I brought him my hologram, and back in the day, they were on glass. So today they're all digital, but back then they were on glass. And as I was handing my hologram to Dr. Goodman, I dropped it, and it shattered. And I think he was so chuckled and chuffed by it that I was so enthusiastic, my eyes got really big, that he hired me. And I worked in his lab from freshman all the way through my PhD.
Oh, wow.
So that was 8 years, Dan, and it was terrific. And I think the reason I mention that is because when I went to Stanford, and it was 8 years, I never had a woman professor in a technical subject. And in fact, in 8 years, I only had 2 women professors total. Lovely professor in psychology, wonderful professor in communicating about science. But I didn't know that I could be a professor because I didn't see it. We'll get back to that in a minute. But fortunately, I had terrific male professors. And I point out Joe Goodman on the left, and also talk a little bit about, I studied lasers and nonlinear optics. So Tony Sigmund, who has passed away, and also Steve Harris. So they're really important because there are a couple lectures, and this is sort of a theme that they gave, that I must have been particularly awake during that lecture, because it actually was what they taught me, and we'll talk about this in a minute, led to starting a couple companies. So I'm going to talk a little bit about Steve Harris, who's in the middle of the picture. He was the lead author on a truly important paper that was published in 1964. It's referred to in the literature as Harris, Oman, and Chang, Steve Harris. And it showed that you could stack birefringent liquid crystals rotated in different directions and get striking optical effects. And so it was a nonlinear optics class, as I mentioned. And if we go to the next slide, I think the next slide. Well, go back for it. Yeah, here it is. This is this paper, Harris, Oman, and Chang, is optical network synthesis using birefringent crystals. And so what was beautiful about this work is that it used Chebyshev polynomials and creating Chebyshev filters, I should say, that was typically we had studied in electrical engineering done at the radio frequencies. He put them in the optical frequencies. That's very important. So I thought that was really cool. And I was just inspired by the possibilities. And think about when this was done. It was in the 60s. I arrived in the 70s. And this was about the same time in 65 that Gordon Moore really talked about his Moore's law, which at first said that he predicted in the next 10 years, the number of transistors on a chip would double every year. He got a little more conservative and backed off. And in 75, he did another prediction, which is they double every 2 years. So think about that. Back in the 70s and 80s, I'm at Stanford. There's about 1,000 transistors on a chip. By 2030, there are as many transistors on a chip as there are neurons in the brain. And that is phenomenal. In fact, one of the great regrets of my career, Dan, I don't know if you feel this way too, because I think we're about the same age, is that had I known in 1980, we knew Moore's law. I guess, did we believe? Had we known and believed, we could have predicted the tremendous amount of information data today, the sensors, the computational power, even quantum computing. And the fact that there's as many transistors on a chip as there are neurons in the brain, about 100 million, you realize that the key is how do we connect those? There are more edge devices in the world than there are people on the planet. That may be for another talk. But anyway, moving on here, I finished my undergraduate degree about the time the computer revolution was brewing. And so there was the TRX, we called it the Trash 80. That was what we called it at the time. It wasn't, of course. It was one of the first, personal computer machines. It was about 1974, 75 that came out. And at the same time, I was able to take classes from Bernie Woodrow, who was the professor that developed the least mean square LMS algorithm, which adaptive signal processing 40 years ago is the AI machine learning of today. So with all of this going on and having these fantastic professors there, it really made an impact. And I really wanted to be a professor. And when I got to the University of Colorado Boulder as a new assistant professor, I had my students read Harris, Oman, and Chang. But I took a slightly different direction on that. We used the same mathematics of Harris, Oman, and Chang, but we looked at outputs at the color frequencies, and we designed a class of components called color polarizers, or 10 elements that we'd stack up, just like those birefringent crystals in the paper that I showed you. But we were able to create Chebyshev filters that had very sharp transitions between the colors. And I think if we go to the next slides, we'll see that. And from there, we could combine them and create blue, yellow color polarizers and red, cyan color polarizers. That gave you the four, if you will, complementary colors. And if you put them together, you can get really neat red, greens, and blue. And you can see these filters on the right-hand side. The exact same mathematics and radio frequencies we just used at the optical frequencies. And we built this whole class of technologies. And it was at the University of Colorado Boulder that I met in the previous slide, a chap named Noel Clark. And from Noel, I learned about liquid crystals. And I had a student, Gary Sharp. He was a very sharp student, still is. And we were able to put these polarizers together with liquid crystals and create a fast switching color shutter, which is what's depicted in this diagram. There's a little Boolean logic that when the two switches are 0, 0, you got green. When they're 0, 1, you got red. And 1, 0, you got blue. And 1, 1, you got black. Well, once you can do RGB black, and then if you do it fast enough, you can merge the RGB in order to get white. You can actually do something pretty neat. And because these liquid crystals were ferroelectric liquid crystals that Noel Clark invented, we were able to do this in microseconds. Well, if you think about the competing technology, if we go to the next slide, and that's just an example of how sharp the transitions were between blue, green, and red. And I'll just stick here for a minute. Between blue and green is cyan, and between green and red is yellow. If you want to get really great color, you want to notch those. So these are notch filters, bandpass filters, again, all designed with radio frequency technology and math, but just done in the color bands. We go to the next slide. So this was the competition for that little color shutter I showed you on the previous slide. It was a 3-gun so-called CRT, or cathode ray tubes. Probably nobody on this talk knows or have seen this before, but these were huge systems, and this is originally how color TV was projected. So I wanted to do something that was much more compact. So if we go to the next slide, we were at this same time, this is now fast forward, we're about in 1987, wanted to come up with a very compact display, not the big 3-gun that we showed in the former slide, but something that's very compact. Well, about that same time, enter the National Science Foundation. National Science Foundation was about to change the way research is done in the world. In 1985, they established the National Science Foundation Engineering Research Centers. And this was in direct response to then President Reagan's State of the Union address that called for cross-disciplinary research focused on big problems that impact society and the ability for the U.S. to regain its expertise in manufacturing. Does this sound familiar? This is in 1983-84. So at the University of Colorado, I co-wrote a grant for an NSF ERC, and we won. And it was in optoelectronic computing systems. And so what we were able to do is look at really important technologies like liquid crystal displays that are now everywhere. And you don't see a cathode ray tube display anywhere. So it was a disruptor. And we developed this class of liquid crystal on silicon devices, or LCOS, which is now estimated to be by 2026, $6 to $8 billion industry. And what it does is that these are chips. So think about Moore's law coming together, the advances of Noel Clark and liquid crystals, the packaging, the manufacturing supported by the National Science Foundation. And we actually developed these, and we were able to combine them with those color polarizers from the work that I learned about when I was a student, and get these very compact projection displays you could hold in your hand. And that was really some of the breakthroughs when you focus on an industry that requires multiple disciplines working at those boundaries. So, I just thought if we go to the next slide, we could combine now that reflective display, and you see LCOS up there, that's liquid crystal and silicon. And with a color shutter, which I showed in a previous slide, that's the yellow, and then a lamp coming in, we could switch very fast red, green, and blue. And if you do it fast enough in color sequential, you can get a full color image. So these are systems you could hold in your hand as opposed to the large portable ones we saw. If we go to the next slide. So this is the National Science Foundation annual report from 1987 that mentioned our work on the right in the optoelectronics computing systems. Phenomenal. Every country in the world has copied these large convergent research translational centers. And it really was a sea change, because prior to that, research was funded usually one professor and a few graduate students at a time. And this was very different. And eventually all the other DOE followed suit, Dan, as you know. When we were working together, they were the frontier research centers and the hubs. And it's been something that's been very successful. Go to the next slide. So this is just an example of this three-panel system where if you don't do color sequential and you want to do them all at once so that you have a brighter system, you need 3 of these panels. And if we go to the next slide, the problem with the components, and this comes up with something else that I learned, is that they were using a Phillips prism. Phillips prism was used in a camera, not in a projection display. And the other problem is, if you look at this, these are all interesting angles, but none of them are 90 degrees, in total, right? One, I guess, the back is, but they're all at different angles, very difficult to manufacture. So this violates a principle of design where you want one item in your component to do one function, because if you have to change it and it does other functions, then it's going to change those other functions and you can never optimize to it. And that was the problem with this particular device. It could never be built for under a couple $100. So you could never get it cheap enough in order to be in the market. And it was done at different angles where each of those surfaces has 2 functions. So moving to the next slide. I learned that from Bert Hesselink, who was one of my professors in the machine shop at Stanford. We go to the next slide. So this was what we designed, which is called the color quad, again, Gary Sharp and myself, where it takes in light from the left, splits it into yellow, blue, then the yellow split into red and green. The blue comes through and it combines it. These were so simple, and the 3 LCOS displays are shown on the beam splitters. We were able to make this for tens of dollars. And we took over the industry. In fact, in the 2000s, the early 2000s, if you went to Best Buy or Circuit City and you bought a front projector, rear projection, it had this technology in it. So we owned the market for about 7 years until we didn't. Another story. So that's when flat panel displays really came over and projection displays took a back seat. If we go to the next slide. These are just some of the examples of the rear projection systems that use this technology. Go to the next slide. So we then started to apply these thin film birefringent elements, to 3D. And we developed the technology that eventually was sold to Real D, which was just recently bought by Sony. And it really jump-started the 3D movie industry. If we go to the next slide. So our breakout movie was in 2005 called Chicken Little. And then the big one was 2007 called Avatar. And that was the first movie, I think, to net $2 billion. I'm just going to conclude with one, if we go to the next slide. This is something that, Dan, you will remember this because we were in the Department of Energy. You were the head of NREL at the time, and I was Undersecretary of Energy. And this was the Deepwater Horizon oil rig when it exploded and began leaking oil into the Gulf. I remember that day very well. It was April 20th of 2010, and it was a Tuesday. And it was actually the largest, I think, oil spill and environmental disaster in the U.S. history. And what was challenging about it at the time, and you may remember this, Dan, is that this happened. 11 people died. 17 people were injured. The oil was spilling out from 5 miles below. And what had happened is that there was a bubble of methane gas that escaped from the well, and it shot up through the drill column, and it burst the seals, which allowed the oil to spill out. And when it did that, it had with it the grout from those seals and some of the sand. And I was, so this happened on a Tuesday. On Thursday, I was at the White House, met the president. We were doing a mentoring on the South Lawn. John Holdren was there, the science advisor to the president. And I had not met the president before in person. It was President Barack Obama. And I was a little nervous, I have to say. And I walked up to him and I held out my hand. And I said, President, it's a pleasure to meet you. And we're doing everything we can about the oil spill. And I thought, why did I mention that? We're supposed to have a nice day with ice cream on the South Lawn with all these wonderful students. And he looked at me as we're shaking hands and he just said, thanks. That taught me something, because I knew what he was saying is, I really need to tell the American people something. Can you help me? And it was inspiring. So I went home that night. I didn't sleep very well. President of the United States says, thanks. I need your help. I woke up at 3 a.m, Dan, and I remembered a paper that I had written with John Sharp, another Sharp student, on particle image velocimetry. And particle image velocimetry is very much like the high school experiment that I did. It's a double exposure experiment, holographic interference, that if you have particles in water, which was our experiment, and you take 2 exposures, by the interference pattern, you can tell how fast that water is flowing. And I thought, why is that any different than how fast would that grit from the grout and the sand and the oil? We do a double exposure. We should be able to tell how much oil is coming out so we could get a handle on how big of a disaster this is. So I called Marcia McNutt, who's head of the USGS at the time. Actually, to be honest, I emailed her about 3:30 in the morning, how crazy the times were. And you may remember this, Dan. She emailed me right back. She was up working too. I said, I think we can measure this with particle image velocimetry. Can we get a system down there? And she said, yeah, in fact, the USGS has the world's best particle image velocimeter that will allow this calculation to be done. The next week, the president walked out to the Rose Garden, told the American people that at least 20 million barrels, 20,000, barrels of oil were coming out daily. And at least it gave us an idea of how big this disaster could be if we didn't get it right when we capped it. That whole program, it took us from April 20th to September 19th. And some of the most gutsy call ever was Secretary Chu capping that. So, I think that I just want to sort of conclude for all the students that and professors that are on the call. You never know when you can make an impact from something you've learned if you're motivated. And I was very motivated after talking to the president. Engineering is such a rich background to do anything. So I just want to say a few words about what we're doing now and move to the next slide. Now president at The Ohio State University, and somehow your career comes full circle. Last week, the National Science Foundation announced the Engineering Research Center called HAMMER, which is hybrid autonomous manufacturing, moving from evolution to revolution. So it's our National Science Foundation Engineering Research Center here at The Ohio State University. And I'm so excited about all the students, faculty, staff, and it's joint with 4 other universities, Northwestern, NCA&T, University of Tennessee, and Case Western Reserve. The chance of bringing 70 different industries together with these 5 universities and all the students, faculty, and staff that work on convergent technology around hybrid autonomous machine learning applied to rapid manufacturing. And from that, if we go to the next slide, what we're expecting is to have multiple companies and spinoffs, just like the ones we did in optics from the University of Colorado Boulder. We anticipate that will happen at Ohio State. So we're getting ready for that with our so-called Boost Camp. This is the President's Buckeye Accelerator. And it's a 6-week boost camp, which helps students get the skills and the background so that they don't make some of the mistakes I did because we didn't have that kind of support at the time to help inventors figure out how to commercialize what they want to do. So I just want to say I'm so optimistic about our future just because of the students that are in our elementary schools and our high schools, and the opportunities and the challenges that we, Dan, as educators and leaders of higher education, get to help empower. So thank you for the time to relive a little bit of my career, talk about some of the impact the National Science Foundation has had because of their engineering research centers and the industries and the companies that came out of this incredible investment in our future. And I thank you.
Great. Well, Christina, I am so inspired by your words, and I know that one thing I don't like about virtual is right now there ought to be a standing ovation and a lot of people clapping. So there is virtual applause. I'm sure of that going on right now. But thank you for those inspiring words, especially as it relates to what motivated you both, to enter the field of engineering. And then a little bit of the journey on how it went. And I think, but takeaways from that is mentorship, connectors. I am amazed at one of your extraordinary skills, obviously, is seeing solutions to problems from other areas of technology so that you can actually connect dots. And so that connector role, I think, is an incredibly important one, and one that, we talk about in terms of engineering being the application of science in many respects, for societal benefit. So, you're the consummate engineer, and in fact, that story and how that journey essentially evolved is really, really valuable. For students of today, what advice or counsel would you provide? Recognizing that when we were students, we spent a lot of time on tools, on figuring out, we learned how to use slide rules, for crying out loud. Today you have all these digital assets that are incredible in terms of progress and technology. What advice, based on the differences of today's environment from the environment that we lived in, would that story either change or evolve, or how would you counsel students today, especially as it relates to students of color and or the underrepresented minority students?
Dan, thank you for the question. I think it's the last piece that I particularly resonate with, because look, you go to college and our students are just moving in this week. We'll have convocation on Monday. They start class on Tuesday. And it's kind of scary. You're first time away from home in some cases. You're not feeling confident. You're not sure. And if you want to be an engineer, be it. Even if you don't want to be an engineer, be it. But anyway, and it's because, but you just you can do it. And I think it's the thing I would say is look at activities. Like I worked in a lab. That gave me confidence that I could do research. If I could do research, taking classes where the answer is in the book, piece of cake compared to trying to figure out answers to problems that aren't in the book. Not really. Look, it's complicated. The other thing, it's not an easy discipline, but it's so rewarding. And I think we've worked hard, and I know, Dan, you and I think about this all the time, to make it a much more interesting and a much more interesting from the beginning for our engineering students. So try to invert it. Usually, like when we went to college, you did your capstone design class on your fourth year. Well, by then, you've either decided to be an engineer or not, right? So try and get involved in so-called capstone design classes at the beginning. Maybe it's, the foundational design class. Mm-hmm. And I think then you see, when you're motivated to solve a problem, you're motivated. Okay, I got to learn this. There's a reason. So find your motivation. And it can be just, hey, I want to know what my dad did. I want to know what my mom did. I want to solve this problem. I want to contribute to climate change, chaotic climate change. So in order to do that, you're going to need to know about modeling. You're going to need to know about AI, machine learning. And I would really recommend every student, no matter what discipline they're in, learn about machine learning, because when you've got a chip that's got as many neurons on it as in our brain, as soon as someone figures out how to connect 1 to 1,000, which is roughly about how each of our neurons is connected to about 1,000 to 10,000 others, through the optical interconnects is what I worked on and other systems. Just what machine learning can do today versus what we thought it might do 40 years ago is unbelievable. So I think those would be two things. One is get confidence by doing engineering work. And the second is, enable yourself with tools like your question. And that would be for me, machine learning and being able to combine the analog with the digital world.
That's wonderful. Christina, I can't thank you enough for sharing your stories. We'll obviously get a chance to share this more broadly with a lot of other folks. Delighted to get a chance to get more acquainted with your past as well as the future. It is inspiring to know that people of your stature have been able to have such a great impact. And I think those stories that we'll continue to tell with some of the other presenters that we'll have in our symposium today will continue to advance that notion that engineering is something that a lot of people can aspire to. Sometimes, even when they don't think they can, but the opportunity to provide societal impact is enormous. With the kind of skills and the kinds of capabilities and technologies that science and research and things have brought about. So now it's a matter of connecting those capabilities with the people, and yes. For us, that's really a tall order, but an important one.
Absolutely. Thank you, Dan.
Well, again, thank you so much for that.